should be on. Thank you for the invitation. I've been very happy to have been here at Fields Institute for the past months. Past month, not months, unfortunately. That's the wishful thinking. Yeah, so I'm going to follow up Ruth's talk, and we're going to switch gears a little bit, but I'm going to try to at least point back whenever possible, although it's a bit difficult because I'm really not coming from the physics perspective, but we'll try. And I should also take this thing off, then probably one can hear me better. And really the title is a little bit of a misnomer, or perhaps promising you too much. By analytic, really what I'm going to focus on is sort of not naive, but a straightforward distributional approach. There's also, I'm going to mention this a little bit, an approach via Colombo algebras of generalized functions, which is actually perhaps more suitable to deal with cosmic strings, because there you don't have the issue that you can't really, well, we are gonna see in a second. I should not say this now because I'm running out of time. So really analytic will be distributional for me. And then the other thing that I want to mention in the beginning, without really going into any details, is of course that there is another approach besides the variations on the analytic one that has recently enjoyed a lot of attention, which is a synthetic approach via Lorentzian length spaces and curvature bounds via triangle comparison, or Richie curvature bounds via entropy conditions and all that good stuff. We had a lot of talks on that by various people, most of which are here over the past weeks and in the seminar. So please go check out those talks. All of them were excellent. And I'm not even gonna name names because I surely would forget someone involved. So that's the disclaimer. We are gonna be sticking with the analytic approach. Okay, then mainly what I want to focus on is, hopefully I would in the end get us somewhere where I can state a Penrose theorem for C1 matrix. And C1 of course is still relatively regular in the grand scheme of things, but anyways, this is where we're going to go. Penrose singularity theorem. C1. Matrix. Still, of course, C1 is below the classical C2 theory, so one has to be a little bit careful what one does with curvature and stuff like that. And we are going to do this. And this goal will inform our focus, because we will mainly focus on curvature and geodesics. And how can we deal with curvature? How can we deal with geodesics? And I'm not going to stick to just C1 for all of this talk. I want to present you some other stuff that we know in even lower regularity, but for the singularity theorems, it's currently C1. That's the sort of threshold where we have proofs. Okay, yeah, I guess that's mainly it. Then I guess we can jump into what sort of the minimal regularity is to carry through this really standard distributional approach. And this minimal regularity, fine. Approach, and this has been done, at least we are going, well, we are going to start by looking at curvature. So for curvature, for causality and for geodesics, that's somehow the fun thing, is that one kind of has to bring all these different aspects together. We can't just have curvature, we also need to be able to deal with geodesics. We also have to deal with causality, And all of these operate with slightly different regularity classes and assumptions. So it's gonna be a lot. But for curvature, this sort of recognized minimal regularity to do this in D prime proper would be something called GT regular metrics. And GT standing for Garrosh and Prussian, who did some work on that back in 87, I guess, is the paper. And I guess it's called strings and other distributional sources in gravity or something like that. So it, yeah. Anyways, GT regular would be H1 log intersected with L infinity log. And I'm going to drop all the log indices from my notation very soon. All of these conditions, we generally only need them locally if we work with curvature. H1 being Sobolev space L2 and first derivatives also in L2. And what else do we need? We don't just need this, we also need a uniform non-degeneracy. Just so that we can take the metric inverse in a sensible way and deal with scalar curvature and stuff like that. And the thing is, what was recognized is that if we have this sort of minimal regularity, then there is a sensible way to write down our curvature in D prime. So for example, then, and just because this is the one that we are using later, although for Richie curvature, one could even go below because one doesn't have to have this additional multiplier by a metric inverse because one doesn't trace. But we are going, for example, look at the Richie curvature, and our Richie curvature tensor just schematically consists of terms that are derivatives of Christoffel symbols and terms that are products of Christoffel symbols. And our Christoffel symbols, again, schematically, are a metric inverse times derivatives of the metric, all under sort of quotation marks. If we naively approach it in coordinates, we have these things, and then we can relatively simply check, well, derivative is in L2, uniform non-degeneracy and L infinity log gives us that G inverse is also L infinity log. So we get L infinity times L2, which is a perfectly fine L2 function, I guess. And then we can take essentially what saves us, that's the point I want to make, is that we don't take any products of these Christoffel derivatives in the definition. And we are all very happy with that. So we get a really well-defined distribution. And even for scalar curvature, where we again then trace with G inverse, there's a way to rewrite this derivative to make things well-defined, and this then gives us a well-defined Einstein tensor and whatever. And I'm already talking about this way too long again, but I figured it was good to put it out there. And what was the point I really wanted to make? Yes, the other point I wanted to make is that it is known that for this GT regularity, not just can you define this curvature in this distributional fashion, but you also retain some minimal stability properties to make it compatible with a Colombo generalized function approach. So if you approximate your metric, for example, via convolution, then the curvatures will, at least in the sense of distributions, converge to the distributional curvature you get if you compute it directly and stuff like that. Yeah. Yeah, yeah. I mean, it's in D prime, not in anything better. Yeah. Okay, so, and I started writing on the wrong blackboard, but we'll be fine. Yeah, we have a Richie curvature, and However, the thing is that I want to mention, and this probably now really ties in with one of the points that Ruth made in her talk, it is known that the singularities, or now I'm using singularities in two different ways during my talk, which I shouldn't do. Let's use regularity. Let's use singularity for geodesic incompleteness and regularity for well, singular supports of these distributions and stuff like that. So it is a known result, and let's put this as a remark. And this also goes back to Gerach-Taschen's paper. And I should probably call it theorem because it's really a theorem. So if we have a GT regular metric, then the singular support, or also just the support of things like the Riemann tensor or the Einstein tensor or what have you. I'm going.
The complement singular support in the open set is smooth.
Yeah. Okay, so the singular support of Riemann tensor or also Einstein tensor, etc., I guess, of all these curvature quantities has at most codimension 1. So it has either codimension 0 or codimension 1. So this particular domain walls or stuff like that, we could really treat in this framework, I would assume. But strings, we really can't. And this essentially comes from the fact that, well, it is just a distribution, but if one looks closely, it has more structure because, yeah.
It sounds like you're saying the singularity could be everything, but that's not what you mean.
I mean, it could, yeah, so this is a bit of a perhaps reverse viewpoint. The singularity, sure, it could be everything. I mean, it doesn't have to be smooth anywhere, I guess. But what you can't have is that it's very, very concentrated. You can't have a Dirac delta that only sits on a two-dimensional hyperplane or something like that. And yeah, unfortunately, I've never looked at the proof of this result, I must say. But I know it's out there, and I know that.
So you can't have smooth.
Wait. Okay. I mean, I guess, yeah. I mean, you certainly can have a smooth situation. Okay, I guess 0 or 1, or it's just smooth. But you can't have the situation where it's smooth everywhere except on a two-dimensional plane or something like that.
So if it was smooth, you would call that then the single support a codimension 4 or something, right?
Yeah, okay, yeah. Let's put if non-empty. Yeah, that's of course. Yeah, but like my understanding of this result is that really it comes from this very specific form that somehow gives you more regularity than just D prime if one looks very, very closely. No, this is without curvature assumptions. I mean, this is general. I guess there's in the paper by James Vickers, I guess there's, or probably elsewhere as well, there's a general statement that if it's a tensor distribution computed from something GT regular that only involves essentially things which are of this form in the composition, then you get this singular support result. So I guess that's kind of where this is coming from. Yeah, so I mean, I don't really know domain walls, but I would assume if you want to model them as delta sitting on a hyperplane, then this would be the case. And I guess if you talk about matched spacetimes, which probably is another name for domain walls, then yes, indeed, my understanding is that they are GT regular. Yeah. 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 Space-time codimension. Yeah, yeah, exactly. Exactly. Yeah.
So you can't do a generic as a singular, what I would call a singular.
Yeah, but it makes yeah, but that's yeah. I feel like singular source makes sense as a terminology because that's essentially, I mean, that would be sort of my perhaps naive original idea if someone tells me we want a string where something just lives on a two-dimensional hyperplane, would be like try and slap a delta on it and see if we get anywhere. But I guess we know that this doesn't work. And I must say I'm still not entirely squared with and maybe I'm also too tired with how this conical singularity then comes in, but I guess, and anyways, I should not talk about this during my talk, but we should chat afterwards. Okay, so we have our GP regular thing, and then just to sort of end this remark, there is possibly a way around, but that I know way too little about, whether this can really be helpful physically via Colombo algebras, so alternative. Where one can really embed distributions, one can multiply as much as you want, so it's a truly nonlinear theory. However, this comes at the price sort of it's would be only products of smooth functions agree with the pointwise products, and once one goes below smoothness in both factors involved, you don't agree anymore. This is of course also a well-known result. So really I'm giving you a lot of background, but only agrees or is compatible with pointwise product. And the other thing, of course, is that the objects are, if they are not actually distributions that are embedded in there, then the objects are a lot more complicated because one has to deal with these nets and can't just really go to the limit. But I guess maybe that's more natural physically anyways. That's also somehow this tension in my head that is not completely resolved between, do we want things to be distributions or do we actually want things to be smooth and just very, very sharp? So, but yeah, I should probably not go there, and I should put a pin in this and continue with my talk unless there are questions. Sure.
Element of the algebra, does it act on fitting functions or there is only for just an element?
I mean, it doesn't really act. It's just algebra, meaning I can multiply elements in it with each other. But yeah, I can embed d prime, and I can embed smooth functions.
Sure.
But yeah. Okay. Then I should check on my time because, yeah, this took a while, but I think it's good to try and make some connections and stuff like that. And then if not now, and of course, this is all going back a long time and really not my work. So I would like to also talk about a little bit about my work and what I've been doing essentially since my PhD, and I'm still kind of working on intermittently, though my focus has shifted a bit, which is really then the singularity theorems. However, yep, then let's actually continue talking about curvature. And we are going to turn up the regularity now to C1 for a little while. So I see. Okay, I'm not gonna use that part. I mean, I've already been talking about curvature a lot, but in particular, I want to tell you a bit about the energy condition. So really, we are now interested in curvature bounds and not necessarily the curvature tensor itself. And I'm going to just give you the definition of the null energy condition that we will need. I mean, need is a strong word, but yeah. So we start out with a space-time G, and just to really put this out there, I guess I did not say, but our manifolds are assumed to be smooth and nice throughout. It's just a metric that will do worse things. Be in C1, and we say satisfies the D prime null energy condition if for any compact K and any positive delta. Yeah, also notation wise, my deltas are not Dirac deltas, they're epsilon delta deltas. Delta positive, there exists an epsilon not depending on delta and K. Let's leave it like that, positive, such that we have the following. Richie ij xi xj is greater than minus delta for all smooth local vector fields X defined on some open U in K, and this is all a little bit annoying and one probably wouldn't need it. However, what's important, we need this for all smooth local vector fields, satisfying two things, that the H norm of X is equal to 1, and I'm going to tell you about H in a second, and that these X are almost null. X is less than this epsilon naught. Okay, I should also say this inequality holds in D prime U. So for scalar distributions on our neighborhood U, I promised you the H. H is just some background Riemannian metric. And note all of this, it doesn't actually depend on H. I mean, theoretically, if I changed my Riemannian background metric, I would get a different epsilon naught. But if it's satisfied for one chosen Riemannian background metric, it's satisfied for all. Then the other thing is two things I want to talk about. Both of these conditions. Let's actually start with this one. Why do we need this? Why can't we just say Richie XX is greater equal 0 for all null vector fields X? Well, first off, constructing null vector fields is a bit more difficult if the metric is non-smooth, because then the regularity of the null vector field will depend on the regularity of the metric. So we probably won't be able to get smooth null vector fields. We may not, depending on where exactly the irregularities of the metric lie. However, if one looks at it very closely, one would see that if G is in C1, then actually Richie is in the dual of C1 functions. So it's a distribution of order 1. So even C1 null vector fields would be sufficient. So one could actually formulate something that more closely resembles the classical null energy condition. However, if one did not have this this kind of openness condition, this would be unstable, and that then doesn't really. So first off, it doesn't work for the proofs, but second, I also think it is desirable to have or to impose curvature conditions that are in some sense stable, because otherwise maybe physically this is not great if it's very dependent on being exactly here and not working well with approximations.
The thing guarantees that I won't be able to find another null vector such that null condition.
Yeah, I mean, null vectors would be okay even if I formulated it with null, because then I would formulate it for all null. No, I mean stability in the sense that if I choose a nearby smooth metric where we just have like, yeah, essentially if I choose a nearby smooth metric, then this nearby smooth metric will satisfy something similar and not have arbitrarily large negative Richie curvature for its null vectors. So kind of, this includes vectors that are null for G, but also vectors that are null for nearby smooth metrics. I guess that's how you could view it. Yep. I mean, it really doesn't matter. It's mainly that we only have to, if we want to apply it, then we only have to, so if we want to apply it, we start with a null vector and then want to extend it to a null vector field. And then the idea is because we only have this, because we only work with local vector fields to begin with, we also only need to do that extension locally, which makes our life easier. I mean, yeah, sure you could. Yeah. Well, for all open Q subset K and all smooth local vector fields defined on yeah, to be honest, if I ever rewrote this, I would just scrap the K and do like open relatively compact U. Yeah, it's very clunky.
That Richie condition would be greater than equal to 0, is that right?
Yeah.
Sorry, so in sloppy language, my sloppy language is you've now put it to minus delta because you're allowing for the fact that the discontinuity might just sort of give it a slight. No,
She's also allowing for the fact that X is not really light here. So
yeah.
if XX is just less than epsilon, it's not equal to 0. So
yeah.
Let's compose 0. Richie lower bound in the light-like directions. But she's saying if I'm close to light-like, then
I'm-
range bound shouldn't be too much below 0.
Okay.
Yeah,
I think
That's
yeah,
exactly what I'm
probably-
saying. Yeah.
I think what might be confusing me here is just a simple convention, actually. So-
Yeah, I mean, it's in the kind of in the quantifiers, but really what I want is greater equals 0 for all things that are actually null. And if I'm not actually null, then I still want to be almost non-negative.
No, but no, sorry, I think I'm just confused because normally I would sort of say, okay, I want T naught naught to be positive. I want T naught naught to dominate all the other components. And so I
Okay.
would, and I'm just trying, I think I may be just a bit too tired to change it to the reaching rather than.
No, well, if we're looking only in null direction,
This would be the same like T, I, J, I.
Well, then I would expect that to be positive for any time like that.
But that's the strong energy condition for time like ones,
Not
isn't it?
Not necessarily. But
Null is only for null vectors, isn't usually?
yeah, but I mean, you can have, the strong energy condition is saying that rho plus 3p has to, or rho plus.
Yeah, okay, that's really the Richie. Yeah.
she's not wanting to do anything with time.
Suppose it in the nulls.
Yeah,
But-
yeah.
but because she's only-
Can I speak from the online audience? We don't hear anything that the in-person
Ah,
audience is saying.
Okay, I see.
So maybe you guys could
Sorry.
ask a question after, and then she can give her talk first, and something like that. I don't.
Yeah, maybe I think we are getting stuck with our quantifiers here in this definition. But maybe it helps if I say if the metric is smooth, then this reduces exactly to the original one that you know. So it's
Mhm.
consistent. Yeah, and I'm happy to talk. Yeah, that was one of the remarks. So it's consistent with the smooth case. And also I really shouldn't say too much more. I do want to say kind of this because this is also maybe weird looking extra condition, but essentially because having a non-zero bound here breaks the scale invariance, I need to have some control on the scale of x because else this never could be satisfied. And the reason for equal 1 and not less equal 1 or less equal c is that less equal would give you a stronger condition because any x that is close to being the 0 vector, even if it's completely space-like, would satisfy this. So we don't want to impose that. Okay. This is that. And I did want to give you sort of the stability statement that comes with it. There's another black. Oh, yeah, I'm just gonna go here.
Is there a race what's underneath your push both forwards or?
Yeah, then let's push both parts up. That is of course a good idea. Okay, and I have till 4 p.m. Yes. Okay. No, I don't understand.
Once you write something on the bottom board, there's no way you can, if you know, you can't push it up and pull something down, you can't see it anymore. So you guess-
Yeah, I guess. But
Just really curious.
we won't.
They're-
Okay, I'm going to start with these ones, but I was hoping I would not need to erase anything during my talk. Thanks, Annegret. Yeah, so lemma stability. And this is actually, I should also say, this definition probably would work even for GT regular metrics in some sense. I mean, one has to maybe then be careful here if one doesn't even demand continuity. But anyways, the important bit is not just to give definitions, but to give definitions that you can work with. And that so far really goes down to the stability things, which we so far only have in C1. Okay, let G epsilon be smooth Lorentzian matrix such that our G epsilons converge to, or rather our G epsilons are constructed from G in a very special form. So epsilon. And actually not that special, because if I gave you an arbitrary thing and asked you to smoothly approximate it, the first instinct would be to do a standard modifier, and that's exactly what we do. However, it's important that we do it via the standard modifier and don't just give general convergence things. Plus, we allow the possibility for correction terms. What we need of this possible correction terms is very good convergence. This need to go to 0 in C infinity log, and they have to do this at a rate greater equal epsilon. So if we estimate them against 0, then there must be epsilon close at least. Okay. Yep. Then for any compact. So that's probably where this compact thing came from, because I kind of knew where I wanted to go, and then it snuck its way in the definition, even though the definition could be made cleaner without it. Then for any compact K in M and delta positive, there exists an epsilon bar of K and delta positive such that, well, for all epsilon less than epsilon bar, again, one doesn't really need this, but the Richie of the G epsilon matrix of XX is greater than minus delta for all X, which are tangent vectors with base point in this compact set K, with a norm X H equals to 1, and which are now G epsilon null. Yeah, and I mainly wanted to state this to remind you of it. Yeah. Yeah, of course. Yeah, this formulation is now a bit suboptimally done, but yes, this is our stability statement. And again, I'm going to just plug someone else's talk. Michael Kunzinger gave a talk in the Riemannian setting where he talked a bit about how one gets these stability statements in general for C1 matrix. His was Riemannian, so didn't have any possible correction terms, but essentially this good decay of the correction terms means you don't lose anything by adding them. And they're mainly due to sort of save the causal structure if necessary. Yeah, and I probably shouldn't say this, but I kind of wanna say it because I remember during Mike's talk, someone asked whether I had a good intuition for why this Friedrich's lemma argument that goes in their works, that the products do converge better. And I still don't have a great intuition, but one thing that which is kind of a bit of the technical / moral reason why this works, apart from the fact that the Friedrich's lemma is a well-known result, is note. Just as a remark, of course, if we have some f which is continuous and we look at derivatives of f smoothed by convolution with this rho epsilon, then yes, this will not converge, and yes, it will diverge. However, what we can see is that this roughly diverges at this 1/epsilon order, because if I put my derivation on the rho epsilon, I get exactly this 1/epsilon. So if I always only have these terms in products with things that can compensate, which is exactly why we need this rate greater equal epsilon in the correction term, then in products we converge better than expected, or the differences of products. Okay, that was the curvature things that I wanted to talk about. Let me talk about geodesics really quickly. 1, 2, 3. And actually, I don't think there's a, so how do I best start this now that I have less time than expected? Let me start by giving you sort of the usual picture. In C infinity, we have the following equivalent definitions of geodesics, or at least causal geodesics, which I guess are all that I'm interested in. Note, however, causal includes null, so we don't want to just restrict ourselves to the time-like case. In C infinity, we have the equivalence between solutions of the geodesic equation and local maximizers. And it is known, and this goes back to, I guess, results by Minguzzi and Kunzinger, Steinbauer, Stojkovic, that this is also true in C11. However, it's also true that below C11, one of these direction fails, namely this direction. So we do not have that solutions of the geodesic equation are local maximizers. And this has a lot to do with losing uniqueness of solutions to the geodesic equation. And there are, in the Riemannian case, explicit examples by Hartmann and Windner that one can Lorenzify rather easily. Let's give it a reference. Where do I have the year for that? Not that it matters, but it's a rather old, 51, I guess that's what I have. Yeah, okay, and I guess if one is really interested in the Lorentzian case right away, there's a nice article by Seemann and Steinbauer where they do the Lorentzian counterparts to these. Okay, below C11, this direction fails. In particular, we have none. Okay, however, and what's really nice is that there is a paper that came out a bit after my singularity theorem stuff, is that actually the other direction does not fail even for Lipschitz metrics. So for 0, 1, we still have this is by Lange, Lechak, and Seemann. Oh. 21, I think now. Yeah. Yeah, that's where I was going to. So for where, okay, this is getting very colorful, but where solution of geodesic equation means Filippov solution. And I probably need to say some words about this, but Filippov solution concept essentially comes from an entirely, I guess, different corner of the study of ODEs. So he wasn't really interested in this for geodesics, but this has been used successfully for geodesics. And the thing is, this works for any L infinity log right-hand side in an ODE, which is exactly what we have in this regularity, and essentially turns the ODE into a differential inclusion. And then, well, we still don't get uniqueness, of course, but we get existence, we get some regularity, and it's essentially nice. Is my understanding of it without ever having actually worked with them yet. Okay. So, okay. Well, I guess I skipped a lot now. So, yeah, I can give you the sort of 2 minutes. What I also wanted to mention is that the Lange, Lütschak, and Seemann paper also includes in sort of this direction statement a regularity statement for maximizing causal curves, because of course solutions of this Filippov geodesic will be more regular. And the regularity statement, they do have a regularity statement even for the 0 alpha. If you parameterize it correctly, then the regularity will be C1 alpha quarters. But since this doesn't really get back to a geodesic equation anymore, because I guess below C0 we don't have Filippov solutions anymore, and one would again have to dig deep into ODE theory to see if anyone has ever studied ODE with even uglier right-hand sides, which people may or may not have done. Okay, and I did want to also give you a stability statement, and I think I'm gonna skip it because 2 minutes is not too long. But essentially what we also have for solutions of the geodesic equation, we have that if we again approximate by, where's my stability lemma here? If we approximate by smooth ones or even just have C1 convergence, this needs much less on the convergence, but then solutions to the geodesic equation will converge to solutions of the geodesic equations. Of course, we can't really tell to which solution they will converge, because now we have plenty of choices potentially. So then 3, 4, 10 rows. Put me up. Of course, the original one going back to Roger Penrose in 1965. So we consider space-time. And G with G in C1, such that we have the following. Hold. If we are globally hyperbolic with non-compact Cauchy surfaces, and I haven't talked about causality at all, but causality is very robust, at least as long as one does not really go down there. If one goes down there, I think causality also becomes a bit more difficult, in particular if one does not have continuous and causally plane, at least. There are things that go wrong, but we are still far away from there. So this is probably gonna be the last thing to fall if we ever get somewhere. D prime neck. I already had hold. And there exists something called a trapped surface. Meaning well, n-2 dimensional closed space-like submanifold, smooth submanifold as with past pointing time-like. Mean curvature vector. And I'm gonna put a picture there, the classical one. So for our space-like 2 surface or n-2 surface, we generally have 2 null directions. And this condition tells us that initially both of these null directions actually converge inward. As past pointing time-like. And then our big conclusion is that there exists a future inextendable null geodesic. Null geodesic in the sense of solution to the geodesic equation. So I think someone, probably me, should go through all of this at some point and figure out that now with the Lange-Lütschak-Seemann result, it probably also works for null maximizer. But then one again has to see what inextendable means. Null geodesic, solution to the geodesic equation, gamma defined on 0t to m with t not being infinity, meaning that it's null geodesically incomplete. And that is our theorem statement, and that is where I will end my talk.
Yeah, that's only story over time. But let's continue this talk.